Today we'll upload the assignments. Okay, I'll make a separate folder in class assignments, and then there you can find it. I will not put it in assignments, otherwise there is, I don't think that submission is mandatory, so I'll upload in the assignment folder on Teams itself. So we started with this phase diagram of a pure substance, and you understand now that what is pure substance. It's a single chemical species whose chemical structure is uniform throughout. And phase means it's a specified mass of substance having uniform composition. It may be multi-component system like ethanol and water example. Okay, but its physical state is uniform and its composition is uniform throughout that phase. So this is a pressure volume diagram, okay, for any real fluid. So you have seen that before this critical point, which is this one, so above this, at higher temperatures, there is no liquefaction, or what you call, there is no liquid phase. Okay, so these are red curves. We said these are isotherms. Okay, and then when you go below this critical temperature, then when you, so this is V. Okay, so when you decrease the volume, okay, or in other words, when you increase the pressure, remember these are equilibrium process. So whatever is the gas pressure inside, the same pressure is outside. So how you will do that process, that's a different thing. Okay, that we can discuss later. That's how you are doing it. Of course, reversibly and quasi-statically. And when you are compressing the gas, the volume will decrease. Gas will get compressed. So it will follow this line. Let's say at a given temperature T. And when there is enough compression, these molecules come closer to each other, and then there is a phase change. And when there is a phase change, so first liquid will come to this point. This point is called, let's see, if I say point A, then point A corresponds to saturated vapor. Okay, and then if you further compress, and then there is a phase change, of course, and then if you further try to compress it, okay, so of course the state variables doesn't change, pressure and temperature, it's a phase change. So eventually everything will become liquid. In between we have a mixture. So if I, as I told you, we will see through examples also, any point in between is a mixture of this liquid, saturated liquid and saturated vapor. Okay, so if I say C contains saturated vapor plus saturated liquid, any point C. And then if I say this point as B, then B is saturated liquid. Okay, and then further you can compress it. Okay, and of course it's very obvious that as you go up, temperature is increasing, so that beyond a certain temperature, kinetic energy of molecules are so high, so that you cannot compress, make it a vapor, liquid. Okay, so this is one remember that this is one experiment or one such curve. When you generate such many curves at different temperature like this, and maybe few more like this, of course they don't cross each other. And then when you make an envelope of these, phase change points, then you create a phase boundary. So this is the envelope. This is envelope of that. So this is one phase line, and this is another phase line. Okay, fine. In between we have liquid vapor both. This is liquid regime and this is vapor regime. Fine. Okay. Acha, this line is saturated stream. Okay, or saturated vapor. What we'll call this regime? Anyone can guess? Have you ever heard this regime? This regime. Let me change the. What we should call this regime? This whole regime. It's called superheated steam. So once you cross this saturated vapor point, and if you further increase the, let's say, temperature or increase the volume, it's called superheated steam. Okay. I hope I am correct and there is no mistake, but we'll see. When we'll see the actual steam tables, if there is any mistake, we can correct it, but I think that's what it is. Okay. So this is pressure volume diagram of a pure substance. Then, sorry, I think we have to click on this one. So this is the same thing. Okay. Now what you see here, this thing, this thing which you see, this will become clear when we will read this equation of state, this what we call it, van der Waals equation. This is the solution of van der Waals equation. And in reality, we know that it doesn't exist. This is not reality. In reality, this red curve is there. Experimentally, you cannot observe it because this is unstable solution. There is a complete mathematical description, which is not the part of this course, but I'm just telling you that if you solve the van der Waals equation of state, it gives you such kind. So this is fine. This matches with van der Waals equation. This is also fine. Means experimental and van der Waals equation solution matches. But in between, van der Waals predicts something else like this, which is not true. What we experimentally realize is this phase change. Okay, so this is the same thing. Okay, this is temperature volume diagram. Okay. So in temperature volume diagram, now you can try that. Now we will draw isobars. Okay, the way we draw isotherms, now we will draw isobars. So it means we'll keep the pressure constant and we'll do the process quasi-statically. We have seen such example yesterday where the gas was expanding against atmosphere and atmosphere was at constant pressure. So that is called isobaric process. Okay. So you take any pressure, you fix it. I mean, throughout the process, you maintain that pressure and then you can increase the temperature. Okay. So one can start either from here or one can start from here also. That's fine. Okay. Great. So how this diagram looks like? So what is happening that you are keeping the pressure constant and you are adding heat to the system. Okay. So when you add heat to the system, it will expand as well as its internal energy will also increase. Fine. So let's say if we start somewhere from here, let's say this point, then as you supply more and more heat at constant pressure, so we are adding heat at constant pressure. Okay, so gas will expand because the heat which you are supplying, some part of that energy will do some work, as well as internal energy of the gas will also increase. So temperature is increasing, but still it is liquid. Then at a certain point, what happens that since the internal energy of the molecules, average kinetic energy of the molecules is increasing, after a certain point, they becomes more free. Means their intermolecular forces becomes weaker, the attractive forces. And then vaporization starts taking place. So this is the point of phase change. So in between, of course, we have both liquid and vapor. So this is saturated liquid point. Okay. And then here we have saturated vapor. And then if you further provide the heat at constant pressure, then again it becomes a complete vapor, and then it may follow any equation of state, not ideal of course, but any other, maybe van der Waal equation or any other equation. There are many equation of states. Okay, so that's how a typical TV diagram looks like at constant pressure. Okay, so you can create such many isobars, right? Like let's say one more, and so on. And then of course this is the critical line. Okay, so there is PC and there is TC. These all are fixed. Okay, you cannot change it. So beyond this, everything is vapor, that you know. Okay, so this is again saturated vapor line, and this blue line is saturated liquid line. Anything in between, this is a mixture of both liquid and vapor phase. Saturated liquid, saturated vapor. Okay, so remember this terminology. This is saturated vapor, this is mixture of both saturated vapor and saturated liquid. This is saturated liquid, this line is saturated liquid line, and this line is saturated vapor line. Okay, great. So this is temperature volume diagram. This is a general diagram for any pure substance. Multi-component system has another complexity. Okay, of course we draw such diagram for those systems also, but that we'll learn in the second module of this subject. Okay, let me open the new page. This is done. Same thing. Okay, just a more informative diagram. So this is, as I told you, this is superheated vapor regime, so there is no mistake. So you have to be very careful while running this whiteboard. And yes, yeah. So this is superheated vapor regime. Okay, as I told you, this is saturated liquid vapor regime, means mixture of both, and this one is called compressed liquid regime, and this is our critical point. That is the rough idea of this phase diagram. So if I ask someone means, let's say if I ask Jagdish, you are there? Jagdish? So Anik?
Yes, sir.
Yeah, Anik, so do you know how we create this diagram? This. So let me, I am drawing it, and just to confirm that you all got it, can you tell me how we are creating this purple line? Just describe briefly.
Sir,
Is this envelope direct or indirect?
sir, we are starting either from the left end or the right end. So slowly we are adding heat if we are starting from left end, and so it is an isobaric process. And when the pressure is same and temperature increases, and
No,
at
I got
some
your point.
point,
Let me again ask my question very clearly. Maybe you are answering same thing but in a different way. I'm saying this purple color curve which I have drawn just few minutes ago. How we
yes,
create this envelope? Very simple.
sir. Sir, in each isobaric line, at
Yeah.
there is a point where it gets converted from, it
So
changes its phase
phase
from
change point, phase
phase,
change point.
it changes,
Yes,
there is a phase
phase.
change, and so
Yes.
we get a horizontal line.
So
The
you got
point
such
from which
yeah.
the
So you got
point
such
from
kind of
which
dots, right?
yes, sir. The
Yeah.
point
And
from which the
similarly here
horizontal
also.
line starts
Good.
and ends, the
Yeah.
locus of such points is
Very good. Locus of such.
the
Yes. So remember, this is an envelope. This is a locus of such phase change point. Okay. From saturated liquid side and from saturated vapor side. Good. That's what I wanted to ensure that you guys got it. That never think that we have created this purple curve directly. You have done these isobaric processes, isobaric experiments on a pure substance, and then by then you got these points, these phase change points, and then when you uh, uh, pass the envelope through all these points, you get this envelope. Good. Very good. Okay. So then again we move. Okay, this is not needed. Why? Because I told you that most of the time we will deal only with this much. So I'm skipping this part. Okay, if someone is interested, I mean, you can, with similar logic, you can create such envelopes. Okay, that is liquid solid transition. I mean, phase change. Okay. Okay, this is PT diagram. Okay. This is not so useful, but I thought since we are doing various phase diagrams, we can discuss it. So I'll just describe what are these things. So this broken green line is for water, which is very unique with water. Otherwise, this solid line is more general. This solid green line for any pure substance. But water has some anomalous behavior. Okay, it has a very deep science, which is not, this is beyond the scope of this course. Okay, this point, red point, is critical point. Okay, critical point means below this you cannot liquefy the gas. Okay, of course, supercritical fluid is not the part of this course. But remember, just as a curiosity or information, so let's say if you want to go from vapor to liquid, this is the boundary. Okay, so one can go this way also. But is it always necessary that we should cross this phase line? Answer is not. There is another way that you can go from vapor to compressed liquid through this path, through supercritical fluid. If time permits, maybe at the end of this course, if time permits, because there are so many things to cover, I'll try to touch this aspect. Okay, otherwise not. So this is the critical point. Okay, everything is written. You can read this diagram later on. This is vapor or gaseous phase. This is liquid phase. This is solid phase. I am sure while preparing for J, you have confronted this diagram because you are aware of the triple point. Okay. So there is something called gas liquid line, liquid solid line, and there is gas solid line also, right? This one, this red line. This is sublimation curve. Okay. But these kind of diagrams are more complex and not very useful for engineering purposes. Okay. This is more from informative from physics point of view, but for engineers, this is not so informative. Okay. So let's move ahead. This is not difficult. You can, if you think about it, you can create this diagram. Okay. But not useful. So let's move. Okay. So this is the temperature entropy. So you all know that from the explanation which you know, that the definition of entropy, you understand it that the degree of randomness. From that point of, although remember the entropy, I'm just introducing this term. Okay, this will come in a proper way when we will start second law. But since we will be needing in the first law also, in order to solve a difficult problem and more realistic problem, so I am introducing entropy also. The notion of entropy which you have, you know it as a degree of randomness. Remember that definition comes from microscopic picture. Okay, what we are doing is macroscopic. We have discussed this aspect in detail, that so there is something called microscopic or molecular description, microscopic or molecular description, like kinetic theory of gases. From there, what you know as degree of randomness, you know it as entropy. Okay, although it's a very vague definition, but that's fine. Now if you see from macroscopic approach, or what we know as classical thermodynamics, which we are studying, it is called classical thermodynamics, and this one is called statistical because it is based on statistics. So statistical. Okay, anyway. What we are doing is classical thermodynamics. In this, entropy is defined this way. ds is very small amount of heat by T, and is small and in a reversible way. So you have to supply heat. That we'll see how. So how we supply heat in reversible way, that we'll see. Supply heat reversibly. So your process should be reversible. So all these aspects will be discussed in second law again. What does it mean by reversible heat supply? Okay. So in classical thermodynamics, that's how we define entropy. Okay. It doesn't talk about degree of randomness. That is microscopic picture. So I thought before, since we are going to use this entropy, before knowing it properly, a rough description is important, and that's why I discussed it. So that is one picture is this molecular picture or microscopic picture, and another one is this classical thermodynamics. ds is defined as heat given to the system by temperature at that given point. Okay, reversibly. For if process is reversible, this is not true, and that is the second law that we will see. Okay, so as you can see that in this diagram we have isobars. So these are constant pressure line. So if you are adding heat to the system, what will happen? That of course its temperature will increase, no doubt, because this some part of heat will contribute to the average molecular energy or average kinetic energy of the molecules. And since T is always positive, and if you are adding heat, its entropy will also increase. From degree of randomness point of view, you also understand that larger is the temperature, more is the higher is the kinetic energy, so more is the chance of more system contains more degree of randomness. Okay, a rough explanation. So as you can see that as if you choose any curve, as temperature increases, entropy also increases. Okay, these are isobars. So again, you can create such diagrams, this TS diagram, and again you will get the same thing, that this is saturated vapor line and this is saturated liquid line. What is interesting to see here, the way you plotted PV and TV, where V was the extensive variable, okay, and P and T are intensive variable. Okay, so on the y axis we are always keeping an intensive variable like pressure or temperature. On the x axis we are putting extensive variable like volume. Here we have entropy. Okay, so that is a general convention which is followed in these phase diagrams, that on y axis you have intensive variable, and on x-axis we have an extensive variable. Okay. So what is important to note down here, that when the phase change starts taking place, then neither pressure, of course, it's a isobar, so pressure is constant, temperature will not also change. That you know, that when there is a phase change, this pressure and temperature doesn't change. What changes? The way volume is changing, entropy is changing. And of course, when you are going to more liquid side, your degree of randomness will decrease, and that's why your entropy is decreasing. So during phase change, remember, during phase change, entropy changes. Although temperature and pressure doesn't change, entropy changes. So if you are going from vapor to liquid, your entropy will decrease. Okay. So many times people miss it during phase change, entropy changes. Okay, perfect. So this is temperature entropy diagram. And as we will cover more and more second law, you will learn to know how we can create. In fact, by your own, you will be able to create such diagrams. You will give a thought. And we can revisit these plots again. But keep, I mean, just giving a rough idea, because we will use such diagrams. Okay. So what is the x-axis? I can't see because this, you know, this screen sharing prompt is coming. What is the, anyone? What is the x-axis here? Is it TS, TV, what it is? Can you see that? Avilas?
No, sir, we can't see. You could just
can't.
hide it. You could hide it.
Oh, I can hide it. Right.
Yes, sir.
Yeah. Thank you. Hide it. This is entropy again. Okay. Yes, thank you. So this is entropy again. Okay. So this is also S. So same thing. I have just put multiple diagrams from various sources so that you can get familiar. It's the same thing. So these red lines are isobars. Okay. So same thing which I discussed, the temperature entropy diagram. This is our saturated vapor line, and this is our saturated liquid line. Then this is saturated vapor regime, superheated vapor regime. Sorry, superheated vapor regime. Once you cross the saturated line, superheated means you are giving means more and more heat to the vapor. Okay, once there is a phase change, you are providing very large amount of heat, and this is compressed liquid, or what we called as supercooled liquid. Okay, and this is of course our mixture regime. This fine. So that's why I put multiple diagram, nothing else. Great. Actually, in this TS diagram, if we take area under curve, what we'll get? Anyone? I have given you the definition of entropy. Can you guess?
Heat.
Heat. Simple. Okay. Because dq is TdS. Great. Let's move. Then this is where, yes, please, Bhavna. Bolo.
Can you please explain the dotted line in the previous one?
Oh, this one? This one, I don't know what they are following. I haven't seen it, Bhavna. I'm not sure what they are trying to convey here. Very sorry.
Sir, this looks like 1 by density.
Yeah, that's fine. But then volume, they are saying, is it a constant volume? I think, of course, it's not. Yeah, so basically, someone has tried to draw a constant volume line, isn't it? Who was saying it? I think so. I have to check. So I would not like to comment on this. But when I took from the sources, I only kept in mind that there are isobars there. So Bhavna, I have to see, because it's just an image from Google, and then I have to go to the source. My guess is that it should be a constant volume line, constant specific volume, right? Who said it's someone said, no? I also think so. I have to check constant volume line. Means along this broken line, specific volume is nothing but total volume by mass of the system. Right, Bhavna? That's what I
Like
think.
specific volume, I guess, because the inverse of density is
Yeah, so I'm saying that specific volume, not volume, specific volume. Oh, okay. You are saying that don't say it. You are right. Constant volume line will be wrong. Specific volume. Yeah, because we are talking in terms of meter cube per kg. Yes, I think you are right. That's what it should be. I think so. Right, Bhavna?
Okay, sir.
Yeah, I mean, I will check, but I'm sure that's what it should be. And of course, creating such more lines like constant volume line and anything else if you want. We'll see in the Mollier diagram, there is something else. You have to do some calculations and you can always create such diagrams. If you have all the data set, rather than thinking anything in terms of scientific explanation that if this increases, what happens to another parameter, you don't need to do that. You can simply calculate these parameters and you can mark these points. And the way you draw graph, when you started drawing the graph, maybe in your 10th standard, where you have X and Y, you can simply draw these plots. Why I'm saying not don't think too much on, like if some parameter is increasing, then what will happen to another parameter? Because for that, then you have to know more laws. We still don't know the second law. So it may lead to wrong conclusion. I mean, you may not get convinced with, or you may not get an answer scientifically. So wherever scientific answer is possible right now, I'm giving you. Where it's not so clear, for that we have to wait for the second one, when all these parameters will be introduced properly. Okay. So I think it should be a constant specific volume line. That's all. I agree. But my only purpose was to show you these isobars. I didn't look at all this broken line when I was taking it from Google. So I have to check. Anyway, I will check. That's not an issue. It will take a minute, but not now. So this is called Mollier diagram. Okay, this is very famous among engineers. Okay, what this Mollier diagram is. So this I will here give you some. I'll try to give you some mathematical description of this. Anyway, this is called HS diagram. This is highlighter. Right. So this is HS diagram. And this was created by this scientist Mollier. So that's why it is also known as Mollier diagram. Enthalpy entropy diagram. This this black bold solid line, which I am making it in different color. So this is our phase boundary. Okay. The dashed lines, I don't know whether I should say broken line or dashed line. Let me mark it with different colors. Otherwise it will be confusing. It's orange lines, let's say. These are constant pressure lines. Okay, as it is written here. And I'm coming to that, how this graph looks like this. Then what else we have? We have, and this is the critical point. What else we have? We have, let me choose another color, maybe blue. We have constant temperature line also. Why these are on top of each other, that we'll discuss. That in this regime, they are on top of each other. That we'll discuss. Okay. Remember, this is HS diagram. So don't think that these lines which I am showing is either pressure or temperature. The pressure and temperature value can be different, but these curves can collapse. These curves can be top of each other. Okay. So that we'll see. First, let me draw, and then gradually you will understand this diagram. Although it's not the right time to discuss this diagram, but I thought, I don't know whether we would be able to revisit this or not. And remember, without understanding this diagram also you can use it freely, but I think we should discuss how we create this diagram. And then again, I think after second law, at least this diagram we can discuss again. Okay, so we have constant temperature line. So these are constant temperature line. Okay, and we have constant pressure line, and these lines are constant quality line. Quality means quality of steam. What does it mean by quality? X. So these are constant X line. And how we define X? Mass of gas phase by mg plus mass of fluid. Okay, that's how we define X. So these are constant quality lines. Okay, so X is constant. Of course, if you are towards vapor regime, your quality is high, let's say, and as you gradually go towards left, your quality of steam decreases. You have more saturated liquid. Okay. So in order to understand this, let's learn few concepts. So let me open now a new page. Now, what we know from first law is as follows. Assume that there is no other form of energy except internal energy. So in place of E, I can write this U. Okay, and it is not dou, this is du. Du plus, that's what first law says. So I said that E contains only U, that's why I can safely write U. Okay. And what is and if we take a simple compressible substance, what does it mean by simple compressible substance? Means the only mode of quasi static work is compression expansion. In quasi-static work, compression expansion of a fluid. So that is called simple compressible substance. So for the such substance, what is work done? Anyone? What is work done? It is also called PV work. So what is work done? Yes. Anyone? What is work done? It's a pressure volume work. What we should write?
PdV.
PdV, yeah, that's all.
Integral PdV.
Yeah, simple. Okay, PdV, perfect. Now, if we do it at constant pressure, so now I am putting a subscript. Now I am doing the process at constant pressure. So, dou Q P. Since it's at constant pressure, I can write du plus PdV plus I can add VdP, doesn't matter. Why? Because dP is 0. So adding 0 doesn't create any problem. Okay. So at constant pressure, and you have done this derivation, I guess, before also. So du plus d of PV. This is only possible when we are doing it process at a constant pressure. So dou Q at constant P is d of, these are all specific variables, huh? Small u, small v, huh? Small u, small p, v. So what we see that, what is the beauty here? You try to see that we know that heat is a path function. We know it. But when you are providing heat at constant pressure in a reversible way, remember, when you are providing heat at constant pressure in a reversible way, and the only quasi-static work mode is this compression or expansion or PV work, then it leads to a state variable, because on the right hand side we have an exact differential, small d, and what we call this, and it means that it's a thermodynamic property. And what this thermodynamic property is? Anyone? D of what? I think you can guess. Anyone?
Enthalpy.
Enthalpy. Very good. Very good. So we know that if you supply heat to a simple compressor, so I'm not writing everything, but you can again revisit the lecture and you can note you can make your own lecture notes. When you are supplying the heat at constant pressure to a simple compressible substance, and if the only work is this PV work in quasi-static mode, then in that case heat given to the system is equal to the change in a thermodynamic property, which we know as enthalpy. Okay, so it means, and that's where it comes that it's an indirectly measurable thermodynamic property, because you have to measure heat given at constant pressure with other conditions which I mentioned. Okay, so it's an indirectly measurable thermodynamic property. So you have to measure this heat, and that will give you enthalpy. So if you do this experiment, and if you add heat slowly and you do the process reversibly, you will come to know your H. In fact, you will come to know your change in H, and then you have to take a reference point, and then we can define absolute H. Remember, for all these thermodynamic property, either it's entropy or enthalpy, you have to define a reference point. Okay, so if you define the reference point, then H is completely defined. You have to just measure the heat given to the system, and you will come to know what is your H. So that's what we learn. Okay, that is point number 1. Okay, I guess I can save these pages also. I don't know. I think there's an option so that later. Yes, it's here. Save. Save. I think desktop and Kausal. Okay. Page 1, let's say. If there will be something important, then we'll save it from on to the page 1. Save. Fine. Okay, another. So that's what we learned, that if we can measure H. New page. Then second law says that if you are supplying heat reversibly, and of course at constant pressure, in the previous process we provided heat reversibly. So let's put this P with us. That is also defined as, or in fact you can say that change in entropy is defined as this. Okay, so we defined two things. So all these are in reversible mode, so that we'll see how we transfer heat reversibly. So we have H, definition of H, we have definition of S in terms of heat. So if someone asks how you measure entropy or change in entropy, we simply say if entropy, then one has to define the reference point. Okay, one initial point, entropy should be known. Known means you have to say that at this point entropy is 0, and there is enough logic to say, there should be enough logic to say that thing. That is not the agenda in this subject. So if you know heat change and if you know temperature, you can calculate both the H and S. And once you have knowledge of both H and S, you can create this Moleau diagram. That is point number 1. Okay. So now we are into that how we can create this diagram. Now we have some idea that yes, H and S diagram can be created if we can measure the heat change and the temperature. Okay, fine. Now what else? If you will see, so if you replace this dou Q P with dH, then what we'll get? This dH by T is ds. So dH by ds is T. Do you think anything wrong here? The wrong, not wrong, but something missing. Remember, we have done this process at constant pressure. It's a partial derivative. You have to write this way: dou H by dou S at constant P, because this relation is only valid if we are doing process at constant pressure. So what we know from here, that dou H by dou S means the slope of this diagram should give us temperature. Okay. Which line, slope of which line should give us temperature? Can anyone comment? Do you have
So the
two
lines of constant pressure.
Very good. Lines of constant pressure, because then only we have a, you see, we have a condition here that del H by dou H by dou S at constant P will give you temperature. So if you draw a tangent at constant pressure line in this HS diagram, you will get the temperature at that point. So it means if you want to create the constant temperature line, then you have to identify all those points at different pressure line where dou H by where slope is same. And when you join those points, we'll get constant temperature line. Again, I am repeating. First, think about constant pressure lines. Okay, so constant pressure line one can easily create, and slope of, at any point, if you take the slope of the curve at that constant pressure line in HS diagram, that will give you temperature at that point. That is point number 1. Point number 2, I am saying that if someone is interested in creating a constant temperature line, then on all the HS diagram at constant pressure line, and we'll see it soon, one has to identify those points where the slopes are equal. And then if you join those points where the slopes are equal, then that will be a constant temperature line, because if slopes are equal, then this dou H by dou S is nothing but giving us temperature. So those are, if slopes are equal, the temperature at those points are equal. If you join them, you will get constant temperature line. So does it make sense, Bhavna?
Yes, sir.
Okay, we will see the more detailed diagram, then it will be more clear. What else I can tell you before taking a break? Let me see. So this is a rough description. Anything else I should, so this is fine. Okay, now let me ask you this way. So let's say that, okay, how we know that this HS diagram or HS curve, any curve should be an increasing curve? Can anyone comment? This HS curve should be an increasing curve for constant pressure line. How? So my question is this, and then we'll take a break. HS curves monotonically increasing.
So temperature is always positive.
Very good. That's all. Increasing at, for constant pressure line, for constant P. So we got an answer already, that dou H by dou S is T, and T is always positive. Okay, in Kelvin, of course. So in that sense, we can say that what we said, yeah, that we will get always an increasing graph. Fine. So that's why these all HS curve are increasing. Now let's one more important point. Consider the fetch this here, this line. Let's say this line. So this we are in this phase change regime. Huh? Do you think it's a straight line? And why? If not, then any comment? So during phase change, will pressure and temperature change?
No, sir.
No, right? It means that during phase change, dou H by dou S slope should be constant throughout, and that's why these lines are straight lines. Okay. And then after that, of course, it's a curved line, but within this, it's a straight line. Because when there is a phase change, then of course, since you are creating isobars, pressure is not changing, temperature is also not changing. And we know that in HS diagram, temperature is nothing but the slope of the HS curve. So slope has to be constant throughout within this regime, in this liquid vapor regime. And it is only possible if you take a straight line. Let's take a break of 5 minutes. It's 10:02. We can meet at 10:07. Okay. चलो break लो, फिर मिलते हैं. So I'll stop sharing so that you will be free. Otherwise, you will be occupied. Huh? Let me stop sharing and then. Oh, where is that button of stop sharing? When you say I should hide it, I already it's not appearing. Anyone can tell where that hide button is?
So one with X on it.
Where? Come again.
Sir,
The one next to
beside
the
the mic
three dots.
options.
One person. Anyone? One. Anyone.